Okay. So in the last class, we were continuing our discussion on the problem of unit commitment, and we finished case 1 as well as case 2. Okay, if you remember, we talked about 3 different cases. So these are the cases. Okay, in the case 1, we followed the priority ordering. It's strictly okay for committing or decommitting the units, and plus additionally we had few more assumptions, like we ignored the uptime and downtime of the corresponding units, and we also assumed that the startup cost is simply the cold start cost. So basically we neglected the hot start cost of the units. In case 2, instead of following the first assumption here in case 1, so instead of following the priority ordering strictly, we relaxed that assumption, and we said that now we will take into account all sorts of combinations possible. Okay, among these all possible combinations, we will take those combinations of those states as the feasible states which are capable of supplying the demand, okay, at a certain hour. So instead of following the priority ordering, we followed the enumeration scheme, where we don't follow the priority scheme. And besides, we also had the assumptions. The other assumptions were kept as the same as case 1. Okay, in case 2, we still ignored the minimum uptime and downtime of the units. We still assume the startup cost as the cold start cost, and we still assume the hot start cost to be negligible. In case 3, we relaxed, or we introduced few more assumptions, like still we were following the complete enumeration scheme. In case 3, we will be considering minimum uptime and downtime of the units. We will consider the hot start cost as well as the cold start cost. So wherever the hot start cost will be applicable, we will apply that. And on the other hand, wherever the cold start cost will be applicable, we will apply that in calculating the cost at a certain hour for a certain state. So case number 1 and 2 are dealt with in an elaborate manner in this lecture, but case 3 will be kept as the assignment. Okay, so case 3, you will find the solution. Okay, you will find probably some help from the textbook for case 3. So taking that help from the textbook, I would like you to complete this case 3. Okay, so it is neither like case 1 nor like case 2, but there will be little differences. Like you have to assume now, you have to consider now the uptime and downtime of the units. You have to consider the startup costs to be either hot start cost or cold start cost. Okay, so case 3, you have to submit as an assignment. Solution of case 3, you will get, I think, sufficient help from the textbook. So how to deal with this uptime and downtime of units, we will take another example for demonstrating this issue today. Okay, so we'll start with this consideration of uptime and downtime of the units, how these consideration actually affects our calculation. We will show that today to start with. So let's go to that slide. So we completed in the last class, we completed up to this point. So there was 8-hour commitment schedule. Okay, you can see 1, 2, 3, 4, 5, 6, 7, 8. So, and we also showed that there is a little slight difference between the progress in case 2 and the progress in case 1, whereas we found that there is a change here in the 3rd hour. Okay, so in case 2, in the 3rd hour, we have to go with state 13, whereas in case 1, we saw that there 13 was not actually a feasible state due to the priority ordering scheme. So instead of 13, we had 14 here. Okay, 14. The remaining ordering was as it is in case 2. So case 3 will be as an assignment. Now to help you out a little bit about case 3, we will give you another simpler example, of course, to demonstrate the idea of minimum uptime and the minimum downtime. Okay. So let's start this example. We have again 3 units, unit A, B, and C. Each of the units have its own minimum and maximum in megawatts. Then each of the units has its own minimum uptime and minimum downtime. We assume that the no load costs are kept to 0 here. Then the marginal cost is basically the incremental cost. Okay. Another name of the marginal cost is the incremental cost. Incremental cost, we have introduced it earlier. But the marginal cost is basically the same as the incremental cost of the unit. Then we also have the startup cost. Here also, again, we are not differentiating between the hot start and the cold start. We are simply taking as whenever any unit has to be started, then this much of cost, $1,000 will be incurred for unit A, 600 will be incurred for unit B, and 100 will be incurred for unit C. Initial status are given. It is assumed that initially unit A is only on, other 2 units are off. So again, in this example, we are not considering any shutdown costs. That means if any units are to be decommitted, there are no associated shutdown costs. So these are the cost curves. You can simply see, you can clearly see that in the x-axis we have the production or the generation. You can say P is the generation of the certain unit. We have 3 units, A, B, and C. Clearly from the slope, you can see that A has the lowest incremental cost or marginal cost. The second highest is B, and the third highest is C. So because they have 0 no load cost, so they will start simply from 0. So when the no load is 0, okay, the generation is 0 for a certain unit, there is no associated cost. So simply this is the graphical representation of these 2 blocks. Okay, so you can see that the slope of this, the marginal cost of unit A is the lowest, so the slope will be the lowest one, and C is having the highest marginal cost, so the slope for the associated unit will be the highest. So clearly it can be seen from here. This is the demand data. This example is only for 3-hour duration. So you have in hour 1, you have 150 megawatt demand. Hour 2 is increased to 300 megawatts. And in the 3rd hour, it is reduced to 200 megawatts. And it is also mentioned that the reserve requirements means the spinning reserve or offline reserves. We are not taking that into account here in this example. So let's check out the solution first. First, we have to go and find out the feasible states. Okay, like the previous example, we have to come up with the feasible states at, because we have lesser number of hours, so we can accommodate it in a single slide. Okay, in the previous example we had 8 hours. Okay, so that would have taken a long larger space in the slide. So here in the previous example we did not show it in this manner, but for a smaller number of hours we can easily accommodate it, okay, in a single slide. So these are the possible combinations. We have 3 units, so we simply order them, not in capacity ordering here. We are simply ordering it like the binary numbering. Okay, so 0, 0, 0, 0, 0, 1, and so on. So ultimately we will reach at 1, 1, 1. Okay, so we simply take the minimum and maximum for maximum combination of each of the states. Okay, so if you have all the units off, pretty clear that your minimum will be 0 and the Pmax will be 0. If your unit C is on only, then Pmin will be the corresponding minimum for unit C, and Pmax will be the corresponding maximum for unit C, and so on. If you have multiple units on, then you simply add their minimums and you put them here. If you have all the units on, you simply put the maximum, add them up and write it down here. So 400 is basically the summation of all the maximum for A, B, and C units, and 210 will be the minimum for the summation of all the minimum for A, B, and C. In this way, you can fill up like the previous example. There's nothing new. So we have 3-hour schedule to be made, a unit commitment or decommitment problem. So we're numbering them like hour 1, hour 2, and hour 3. Our demands, this is the demand. Okay, so in hour 1, the demand is 150 megawatts. In hour 2, the demand is increased to 300 megawatts. In hour 3, the demand reduced to 200 megawatts again. So what we are doing here, we are actually trying to find out at each hour which states or which combinations are basically the feasible states or feasible combinations. So let's check out. So that as the demand is 150, okay, so this cannot be a feasible state because it doesn't have sufficient capacity. This can maximum produce 50, so it can satisfy 150. On 100, it cannot satisfy 150. 150, yeah, it can satisfy. So this will be the feasible state in our number, one of the feasible states in our number 1. In this one, you see the minimum is 150, okay, and also the maximum is 250, which is higher than 150. So the demand is actually within Pmin and Pmax. Okay, actually it is exactly equal to Pmin. So okay, it is within the range. It is within the range. This is the keyword. This is within the range of this Pmin and Pmax. The demand 150 is within this, at the range or within the range, whatever is the case. That will satisfy the criteria for being a feasible state. So this one is another feasible state. This one, although the maximum available capacity is higher than the demand, but you see, actually we have to at least generate 160 to run this combination, whereas my demand is only 150. So again, this will not satisfy. This doesn't fall within the range, okay, not even at the range, at the boundary. So to be a candidate feasible state, the combinations or the demand should fall either at the boundary or within the boundary. Okay, this is the clause. So if that condition satisfies, then that will be considered as feasible units, otherwise not. Sorry, feasible states, otherwise not. So accordingly, the upper 3, you see the lower is 160. Here the lower is 200. That means at least you have to generate 200, but your demand is only 150. So why should you go for that? Okay, that means if you follow this, you are actually losing 40 megawatt at least. Okay, you are losing 50 megawatt. If you are trying to satisfy this, why we don't choose this? The reason is that if we choose this one, let's say, okay, 200, the combination this one 110, so at least you are losing 50 megawatt because the demand is only 150, but the minimum that you have to produce is 200. So at the very beginning, you are actually losing some power as a loss. So that's why we don't choose this. Okay, it's not economic. It's straightforward. 160, you are losing actually 10 megawatts. Straightforward. We don't want to choose this. 210, it is higher. 60 megawatt, you are straightforward losing at the very beginning. So we will not choose them. Okay, and in the lower ones, these 3, the last 3 here, these 3, they don't even satisfy. They don't have sufficient capacity of 150. So thus they do not satisfy. So in this way, we actually count the feasible combinations. We consider the feasible combinations. Any question? How do we choose the feasible combinations here? I have explained the first hour, and accordingly, you can also judge, or you can also check the remaining combinations, or remaining feasible states for hour 2 and hour 3, respectively. Any question? Of course, you can check, you can have a little check at this, and we can proceed on. No question. So that means it's clear. So now we go for the feasible, we'll go for the transition because we have 3-hour unit commitment problem. So we have to find out what could be the possible pathways for progressing from 1 hour to another hour. Okay. So from hour 1, from the initial state, okay, what are the possible choices? The possible choices are this, because you see uh, the feasible combinations in total out of these eight combinations there are 8 combinations, okay, 2 to the power 3. Out of these 8 combinations, how many combinations basically satisfy, or how many combinations falls within the category of feasible states? 1, 2, 3, 4, 5. Okay, so all the other states, these the last 3, they do not satisfy, they do not fall into any sort of feasible states in any of the 3 hours. So basically I have to only deal with this 1, 2 in the first hour, these 3 in the second hour, and these 3 in the third hour. So any possible transition could be between any combination between them, right? So I can either go from the initial state. Let's say the initial state is here at hour number 0. Okay, so at hour number 0, the initial state is what? 1, unit 1 was on. Yeah, so unit A was on, so 100. So you see, we check back. So you see the initial status in slide 58 is given. So initial status is 100. Okay, A, B, C, 100. So the initial state is basically this state, 100. So this somewhere here we will be having our initial state at our number 0, and from there on we have to find out which pathway will give us the most optimum progress. Okay, most optimum progress throughout the hours. So you have to only deal with 1, 2. You see, this one and this one are the same. So this is the third different one. These and same. Fourth, these are same, and fifth. So these 5 states are to be taken into consideration. Other remainings are not drawn in the next slides. So accordingly, we have taken this 1, 2 in the first hour, 1, 2, 3 in the second hour, and 1, 2, 3 in the third hour. And they are drawn in such a way that basically they are aligned like this. So 111 is at hour number 2, a feasible state. 110, another feasible state at hour number 2. 101 is another feasible state at hour number 2. And hour number 1, the feasible states are only 100 and 011. So accordingly, we have only taken them and we have aligned them with the table just for clearer understanding. So as I said, we can have transitions from the initial state at hour number 1. Either we can choose this path or we can choose this path. Okay, this completes the possible transitions. Then from hour 1 to 2, we can either choose this one from this. I can choose this, I can choose this, or I can choose this. Similarly, from this one, I can choose this one or this one or this one. And similarly, for between hour 2 and 3 transition, I can choose from here, the topmost one, I can choose any of these 3. From this one, I can choose any of these 3. And from this one, I can choose any of these. These are the transitions between feasible states or feasible combinations. Remember, we have not yet applied any constraints. Okay, remember, we have the constraints here. On only constraint here is the minimum uptime and downtime. Okay, minimum uptime and downtime. Okay, from the next few slides, the constraint applied will be uptime and downtime, and the constraints that the generation should be at least equal to the demand. That constraint is already considered in slide 61 here. Okay, in this case, we have considered that our combinations should be able to satisfy the demand. Okay, so that constraint is taken into account here, and the minimum uptime and downtime will be taken into account for in the next few slides. So let's continue. This one I have discussed already, slide 62. So in slide 64, in this slide, we will try to find out which are the infeasible transitions. What is the condition? The condition is that the transitions which do not satisfy this minimum downtime of a certain unit, either unit A, B, or C, those transitions will become infeasible, okay, or invalid. We can't progress in that direction between any two consecutive hours. So let's start from hour 1 to hour 2, because from here to here, okay, can we progress? Let's see, can we progress? You see, this state was where this was 100. The initial state was 100. So if I stay in the same state in the next hour, I don't have to think about any uptime or downtime. So that means it is a feasible state. Okay, so the feasible transition. What about this one? What about this one? So to come from this state to this state in hour 1, we have to what we are doing. You see, we are coming from 100 combination to 011 combination. Okay. So what we have to do, we have to shut down unit A. Okay, we have to shut down unit A. Now, because we don't have any information about any previous instance before this, we don't know how long unit A has been on, right? We don't have any information before this. So so we don't know, as because we don't have any information related to unit A or how long it has been turned on. So we can't say too much about this transition, whether it is whether it will be hampered due to this uptime or not. Okay, what I say is we are considering here downtime, but if, let's say, instead of downtime, if I had to consider about unit uptime, 100 means unit A was up. Now if I go for this transition from here to here, I have to shut down unit A and I have to turn on unit B and unit C. Okay, so unit B and C are off. This information is available. Okay, they are off, but again, we don't know how long they are off. We don't know how long they have been off. So simply we will take it as a feasible transition, okay, because we don't have any previous information before this. So the first hour transition, we will take it as feasible because we don't have enough information to justify their feasibility at this point. So we'll simply assume them to be feasible. Now the focus shifts from what will happen. Can I take all the paths from here to here, from anywhere, from any of the nodes, from hour 1 to hour 2? Let's check. So the topic here is, or the condition here is explicitly mentioned, minimum downtime of unit A. So what to do with specifically downtime of unit A? Let's see. The downtime of unit A is 3 hours. Okay, and uptime of unit A is also 3 hours. Downtime of unit B and C are both 1 hour. Okay, both 1 hour. Okay, so so let's now check this one. Let me put some markers, red colors. So talking about this one, okay, can we have a feasible transition here? What does it say? This says if I want to go from this node at hour 1 to this node at hour 2, then what is the transition? Let's check. I am in 100 state and I have to go to 111 state. Okay, 111 corresponds to this node. So that means unit A status is unchanged. Unit B has to be turned on and unit C has to be turned on. Now within this hour, we know that unit B and unit C has been or was turned off. Okay, so from this hour to this hour, the only downtime is 1. Okay, 1 hour, 1 hour. So that means from 1 hour to the next hour, I can turn on unit B as well as unit C because both of their downtime or minimum downtime is 1 hour. So from 1 hour to the next hour, if unit B were off, in the next hour, I can turn it on because the downtime 1 hour has been satisfied. Similarly, if unit C is off, I can turn it on in the next hour because the associated downtime is 1 hour only. So this transition is a feasible transition. Okay, this transition is a feasible transition because in 1 hour, unit B and unit C can be turned on. If in the previous hour they are off, within 1 hour they can be turned on. So that's why this transition is a feasible transition. Okay, let's see next from this hour, from this state to this state. So I'm talking about this one now. What is the transition? From 100, I have to go to this one, 110. So again, what is the transition? Only in unit B. So in 1 hour, within 1 hour, unit B can be turned on because unit B was off here. So in the next hour, it can be turned on. Okay, so you see unit B is only changed. You can see unit B here was 0. Here in this state, it is 1. The remaining, this 1 is still 1. This 0 is still 0. So you have to only think about the transition of unit B. Okay, change of status for unit B. So in 1 hour, it can go from 0 to 1 because the downtime is 1. Okay, so it's a feasible transition. Are you getting the discussion? If you have any confusion, you can stop me and you can ask. Okay, so next, this one. Okay. Now, can anyone tell me, is it a feasible one? I'm in 100 and I have to go to 101. So is it a feasible transition? Anyone?
Yes, sir, it's feasible.
Why?
Because you only have to turn on unit C, right?
Exactly.
But unit C has only downtime of 1 hour, and
Exactly. That
that's
condition has been satisfied. Okay, 1 hour, within 1 hour or after 1 hour, I will consider this that 1 hour has elapsed. Okay, while transiting from one to the next state, I will consider that 1 hour has been completed, the required 1 hour. So this one is satisfying the downtime, minimum downtime for unit C. So this is a feasible transition. Good, thank you. Now come to the next one. Come to the next node. So this node, from this node, I can have all the transitions which are feasible. Okay, so then from this 1 hour one, from this node, I can have all feasible transitions to the next hour. What about this one? Let's start with this one. Yeah, anyone now you can help me out. Because the algorithm has been mentioned, so you can just check whether that's satisfying or not. So now this is 0, 1, 1. Okay, so unit B, remember I have aligned them, I have stretched the table in such a way that it is better understood from the diagram. So we have 0, 1, 1. So unit A is off. Okay, so now unit A is off at this state. Unit B and C are on. So from here, if I want to jump to this node, what I have to do, I have to turn on unit A, right? Unit B was on here. It is still on here. Unit C was on here. It is still on here. But I have to turn on unit A for a feasible transition. Can I? No, because within 1 hour, I cannot turn on unit A. You see, unit A downtime is 3, encircled here in the table in the middle. So 3 hours has not elapsed. There's only 1 hour has been elapsed. So this transition is not feasible. Clear? Unit A has been off for 1 hour only, because in the previous hour, here unit A was on. Here unit A was off, but from here to here, only 1 hour has elapsed. So I cannot turn on unit A within 1 hour of downtime because it needs at least 3 hours of downtime. Clear? So this is not a feasible state, feasible transition. What about the next one? What about this one? Again, go and check 011. Here I have this state 011 current state. I have to go to 110. Okay. Again, my A was off here for the last 1 hour. Okay, because here it was on. Here it is off. A is off. So so A was off here. So I can't turn on A in the next hour. Okay, irrespective of the remaining ones, I can simply check only one unit whether any one condition fails, that satisfies the infeasibility condition. I don't have to check others. So for A only, if only I start from A, let's say, A cannot have a transition of off to on within 1 hour. So it cannot be a feasible transition. Okay. What about this one?
Sir,
Yeah.
for example, in this case, if we suppose that the condition of A is satisfied, and we have to go from C1 and then to C0, we have to consider the minimum downtime or minimum uptime.
Sorry. Can you specify a node?
I said, for example, if we transit from 011.
011. Okay. Yeah.
To 110.
011 to 110. Yeah.
Yeah, considering that A state is feasible, considering.
Yeah, let's say if A is feasible,
yeah.
if A is feasible, now then I have to check all the transitions. Okay, all the state flippings. I can't.
Like,
yeah, let's say, let me continue. Let's say if A is satisfied, for example, A is satisfied. Okay, done. Then you check B. You find that, well, B is also satisfied, for example. Now you check, well, C is not satisfied. Okay, for the given data, C is not satisfied. Then again, it is infeasible. For any transition between any of the states, for any units, if there is only one infeasible transition, then the whole state transition becomes infeasible. So that should be and condition, not or. Okay, you get my point?
Yes, sir. My question is like about which state do we have to consider, downtime or uptime for this
look,
case?
Look. The downtime and uptime depends the flipping of the bits. If you are on, okay, if you are on means you are in up state. So if you are going from 1 to 0, you have to check the uptime, how long you had been up. You get my point?
Okay.
How long you had been up. If you are going from 0 to 1, that means 0 means you are in the down state. So before transition from 0 to 1, you have to check how long you had been down. Get my point?
Yes, sir.
Okay, thank you. So this again it has a problem because you see 0 to 1 transition is not possible here. So for unit A, so this is infeasible. So actually you can see that all the possible transitions from this node at hour 1 to all the nodes in hour 2 are infeasible. So you can say that basically this node cannot continue its journey onwards. So you can say the whole node is basically an infeasible node. Okay, because there is no way to go forward from this node. So simply you can discard this node from your future calculations because it can't help you to progress from hour 1 to hour 2 even, let alone to hour 3. So you see that specifically, although in this example, the minimum downtime of unit A is of prime importance, but it can happen for any other units. Okay. For this example, they have arranged the numbers, the values in such a way that only one unit is of main focus, of prime concern. Okay. So now we go, and what we'll do in next slide, let me check. Yeah. So we will discard these dotted paths, okay, dotted transitions, because they are infeasible. So we'll take them out. We'll discard them from our diagram. So you don't see them. Okay. So you don't see any transition from this node. Okay. So it's out of question. Only transition possibles are these three, from our 1 to our 2. Now we are in a position to go forward from our 2 to our 3. Okay. So now again we check which are the infeasible transitions. Let's check this one first, from our 2 to our 3. Is it a feasible transition? Let's see. We are in 111 situation. Okay, at this point 111. This node belongs to 110. So unit C was on. So I have to check uptime. Okay, uptime, because unit C is on. So I have to check for how long it had been up. So it is up in this hour number 2. It will go into down states in the next hour, in our number 3, for this transition to be feasible. Can we do it? Yeah, our uptime for unit C is also 1. Uptime for unit C is also 1 here in the table, middle table. So within 1 hour, I can switch between on and off for unit C. So this is feasible. Other two states are unchanged. Other two situation unit status are unchanged. So I have to only check this flipping from 1 to 0. So because it is in the on state, I have to consider minimum uptime or on time. So because it is 1 hour, so I can flip it from here to here. So here I'm flipping from here to here. So it is a feasible transition. Now the next one, can we have a transition here from this to this? So again, we check what is the current situation. 111 is the current situation at this node. What is the situation here? It is 101. So A and C are unchanged. If I compare this one, 111 with 101 here, down here. So unit B was on. Now it has to be turned off. So can we do it?
No, sir.
How long does it take? It takes 2 hours. Okay, so unit B is on now, so you cannot be. What is the situation of unit B in the previous hour? In the previous hour, you see unit B was off, right? Because now we have 2 previous hours to consider. I have to consider 2 previous hours. So unit B was off in this hour. It just turned on in this hour. If I had a transition from here to here, it was just turned on at this hour. So only for the last 1 hour, unit B has been turned on, because I have to check from here to here. Here B was turned off. So it is turned on here. Only 1 hour has gone if I go from here to here. Okay. So, but it needs 2 hours. 2 hours to be turned on before I turn it off again. So this cannot be a feasible transition. Okay. Now we continue like this. Can we do this? This one. 111 is the current situation here, and this is 100. So again, I have to turn off unit B within 1 hour. So it can't happen because 2 hours has to be elapsed. So it is not a feasible transition. However, C can transit. C can have a transition in 1 hour. Okay, C was on. We can have 1 to 0 transition because C uptime for C is 1 hour. So this is feasible. 1 to 0 is feasible, but the middle one, this 1 to this 0 is not feasible. So that means the total transition becomes infeasible. So in this way, you can check, you can continue checking. Okay, you can continue checking and you can find out what are the feasible transitions and what are the infeasible transitions. Of course, the feasible transitions are put in with solid lines, whereas the infeasible transitions are drawn with the dashed lines. Okay. Okay, I will allow you, let's say 2 minutes, just check this. Okay, just if you have any query, you can ask it after 2 minutes. So just go through these transitions and try to find out whether you have understood this correctly or not. Okay, so any confusion?
It's clear, sir.
Oh, it's clear. Very good. So let's continue. Okay, so what we have done here, from whatever information we have gathered from all these few slides, okay, so we have actually got rid of, yeah, in this slide we have got rid of all the invisible transitions. Okay, so all the solid lines are remaining here, all the dashed lines are gone, and also what we have done, this whole transition is invisible. Okay, the whole node becomes invisible choice, so this will also be discarded, so we'll be only left with this remaining solid lines. So these are the feasibility testing, okay, feasible state testing. Now we have to calculate the cost. Okay, we have to calculate, okay, in which way, if in which way we will basically go for the optimal progress. Okay, which direction or which path will take us to the optimal progress from initial state up to our number 3. And for that we have to calculate the costing. Okay, so again, what we do, we actually give the node numbers here, additional node numbers. Okay, 1, 2, 3, 4, 5, 6, and 7, just to help out in calculating. So we have now added the corresponding node numbers at the 3 different hours. So how many states do we have? Okay, or how many nodes basically we have remaining? We have 7 total. 1, 2, 3, 4, 5, 6, and 7. Out of these 7, the first node belong to our number 1. So this one basically only covers load of 150 megawatt, which is the load for our number 1. Okay, state 2, 3, and 4, they belong to our number 2. Okay, 2, 3, and 4, these 3 nodes or these 3 states, they belong to our number 2. So they will have a common load. In our 2, we have how much load? We have 300 megawatts. So these 3 belong to basically our number 2, and the last 3 belong to our number 3, where we have load of 200 megawatts. So in this way, we have listed them. Okay. Now we have to get the economic load dispatch solution. So that these three columns basically gives us the information that, well, for satisfying this demand, how should the generation be distributed among the available units? Okay, among the available units. So state 1, 150 megawatt demand. State 1 is basically, where is state 1? State 1 means 100. State 1 and 5, they both belong to this combination 100. This is A, this is B, this is C. So that means in state 1 and 5, I have only available unit A. Okay. In state 2 and state 6, I have unit A and C available. In state 3 and 7, I have unit A and B available. And at state 4 only, I have all the units available. Okay. So while I try to solve the ELD by some algorithm, of course, then I have to keep this in mind that, well, at each of the state, I don't have all the units available, but I have different combinations of units available at different states. So keeping that in mind, these 3 columns are actually filled up. How? Let us see. So remember, state A gives me only unit A available. My load is 150. So I have to satisfy this load from unit A. Okay. So 150 would be taken from unit A. So the total demand will be supplied by unit A. What is the cost? Remember, there is no load cost. No load cost is 0. So if I take 150 from unit A, so simply you multiply this by the marginal cost to give you the total cost. So 150 here, this demand multiplied by the marginal cost of that unit is 150 multiplied by 10. So it gives you 1500. As simple as that. State 2, we have unit A and B available. Sorry, unit A and C available. So what you do, you remember this algorithm actually I discussed earlier. What you do, you take whatever is available, whatever maximum is available from unit A, if possible. So here it is possible because I can take 250 because my demand is more than 250. So I can take 250 and the remaining is taken from that is also actually the maximum of unit C incidentally here. So I can take 250 from this one and 50 from this one. That equals my demand. So I can take 250 from here, 50 from here. And simply you calculate 250 multiplied by 10 plus 50 multiplied by 20. That will give you this 3500. Then at state 3, demand is still, because we are still in these three states belong to our number 2. So their load demand is same. So then PA, it is still, so the combination is now 1 1 0. Okay, you see 1, so it is on, so 1 1, this is 0. So it's 1 1 0. So again, can you take 250? You have to check the minimum of PB. What is the minimum of PB? Yeah, it is 50. So I can take 50 out of this here, and the remaining is also the maximum of unit A. So I can take the remaining. However, let's say, for example, B the minimum of B were, let's say, 70, what you would have done in that case? How would you distribute the demand? Anyone? To the view. Oh, yeah. What you would do if, let's say, the minimum of, yeah, here it is basically listed. So let's say the minimum of B was 70 or 60. How would you have distributed the demand, distributed the generation here? We were, yeah, here. If B units minimum was 70 or 60, more than 50, how would you distribute this among them? This has been discussed earlier for some other example.
Will operate unit B at its minimum
Minimum,
power, and
yeah, and the
then
remaining
use
has
that.
to be taken
Yes.
from unit A. Thank you. So the minimum has to be satisfied for each unit, as well as the maximum, of course. So because if B units minimum was anything higher than 50, then I can't take 250 for unit A. So I have to reduce this, and I have to set this one at its minimum and take the remaining from this unit. Okay, so in that case, this would have been, let's say, if the minimum of unit B were 70, then I would have arranged this in such a way: 230 here and 70 here. Okay, and correspondingly, I would have to calculate the cost. So here again, the calculation of cost is simple. You multiply 250 by 10 and 50 by 12, add them up, so you get 3100. So in this manner, we can complete this table. Okay, it's straightforward. So in the next slide, what we do, whatever cost we have calculated here, these are basically the production cost or the generation cost only. We have not attached any startup cost yet. So we have only calculated the operational cost, or we can say the generation cost. So we have simply added them to each of the nodes. Okay, so for node 1 or state 1, we have attached $1,500 and so on. Whatever is calculated in the previous slide, we just appended them to each of the nodes. Now here, we incorporate the startup costs also. So here in the table, in the right table, you can see we have copied it. We have reproduced it here, okay, for our convenience. So startup cost for unit A is $1,000, unit B is $600, unit C is $100. Means if you want to turn on unit A from off status, then you have to spend $1,000. If you turn on unit B from off state to on state, then it would incur $600, and similarly $100 would be required for turning on unit C from off state. So, so these blue colored numbers are basically your startup cost, whereas the black colored numbers, digits, are the operational cost or the production cost or the generation cost, you can say. So let's focus on these blue colored numbers here in this slide. So startup cost. So because from the initial state to this state, we are not changing our status state, okay? None of the units have changed its status, so there is no startup cost, zero. From this one to this one, from 1 to 4, what is the transition? From 100 to 111. So I have to turn on unit B from 0 to 1, and I have to also turn on unit C from 0 to 1. So I have to add up the startup cost for unit B and unit C, because I'm turning on both unit B and C for this transition. So this 700 is basically the summation of the startup cost for unit B and unit C. Okay, so this is 700, explanation of 700. From here to here, what is the transition? 100, 110. I'm turning on only unit B. Okay, so unit B is 600 startup, so this is the 600 startup cost. From here to here, what is the transition? 100 to 101. So you see unit C is only turned on. So unit C startup cost is 100. So I'm simply attaching it to this path, $100. This part is done. Now from here to here, from 4 to 7, what is going on? 111 is at 4, 110 is at 7. So I'm only shutting down units. So we have told earlier that we are not considering any shutdown cost for this example. So because I'm only shutting down a unit, so I don't have to spend any money there. So it is 0. From 3 to 7, it is the same state. So I don't have to bother about any startup or shutdown cost. So it is 0. From here to here, what I'm doing, 101 to 110. So I'm shutting down unit C where I don't have any cost because no shutdown cost is there, but I'm turning on unit B. So there is some cost, $600. So this is your $600 from here to here. From here to here, it is the same state. So don't have any cost. From here to here, I'm shutting down unit C. It is state 2 belong to 101. State 5 belong to 100. So I have to shut down unit C from 1 to 0. So it is shut down. There is no cost. So there is no cost, 0. Okay. Now I calculate the accumulated cost. I add up the costs. How do I do it? So if I am here, I have to add up the operational cost at this node plus any startup cost for transition or any state transition cost. So because there is no state transition cost, so I will simply add 1500 plus 0 becomes 1500. So in the pink color, we have shown the accumulated cost here. This is the legends. Accumulated cost is in pink or whatever reddish color. Blue is the startup cost and the black one is the operating cost. So then 1500 is the accumulated cost. So then what is the cost here? If I go from here to here, how do you get 5400? How do you calculate this cost? Anyone? My production cost here is 3200. Okay. My state transition cost is 700. So that makes it 3900. Okay. 3200. This is basically the dynamic programming algorithm. This is basically the dynamic programming algorithm. So 3200 plus 700 is 3900 plus whatever cost was there in the previous state is 1500. So simply you add 3200 plus 700 plus 1500, that would give you 5400. Similarly here, you calculate 3100 is the current status cost, production cost, plus the state transition cost is 600. So that makes 3700 plus 1500, that gives you 5200. And similarly, you can calculate cost. Okay, you can see one interesting point here is you see some, again, dashed lines there. Okay, some dashed lines. Means what? So you see at node number 7, to reach at node number, the attendance is the startup. Okay. So you see at node number 7, we can reach in 3 different ways. Okay, starting from here, we can reach through this path. We can reach through this path, or we can reach through this path. However, for 6 and 5, there are no options. So now if you have multiple options, you remember the dynamic programming algorithm, if you have multiple options, you have multiple costs associated with one single node, then you have to choose the minimum cost to reach there. Okay. So what is the minimum cost? The minimum cost is actually highlighted here in pink color, which is this solid line. Okay. This solid line. The operational cost here, or the production cost here, is 2100 at node number 7. Then this transition, okay, if you want to transit through this way, whatever cost will be available, calculated. And if you transit from this way, whatever cost will be calculated, that would be higher than this 7300. That's why they are the higher cost options, okay, higher cost paths. So they would not be, come into picture. They will not be appearing in the picture because I will go for the minimum cost path. Okay, you get the point? So the explanation is given at the bottom that 4 to 7 and 2 to 7, that means 4 to 7 transition and 2 to 7 transition, these incurs higher cost. So I will go for the least cost path. So this is the least cost path in the solid color. Okay, and if you calculate it, you will get 7300. Of course, you can calculate the other two, and you will find that this path and this path gives you higher costs than 7300. So they would not be considered further. Okay, and the remaining actually you can calculate. Okay, the same process as I mentioned, because there is only one path to reach at 6 as well as at 5. So you can simply calculate them, and they would come as 7200 for node number 6, 7100 for node number 5, and 7300 for node number 7. Now this ends our 3-hour calculation. So at the end of our 3, what will be? Yeah.
I consider from state 2 to state 7.
Yeah.
We have 5100.
51.
If we add it up with 2100, the result being 7200 is lower than 7.
No, you are forgetting this 600 state transition. Okay.
Okay.
Yeah, there is a state transition cost. So you have to add up. So that will become 7800. Okay.
Yeah.
Okay. Thank you. So by the end of our 3, I have to decide the final decision. What would be my optimal route starting from the initial phase up to the 3rd hour? So I checked that, well, the accumulated cost here for node number 5 is the lowest cost. So my optimal path would be this one, from 0 to 1 to 2 to 5. Because if I compare these 3 between 5, 6, and 7, the least cost option gives me 7100 after satisfying all the given constraints: minimum uptime, minimum downtime, startup cost, operational cost. After calculating everything, I reach at a solution which gives me this 7100 is my optimum path. So it is mentioned here, again highlighted here. I have erased all the other costs just to make things clearer. So I have only listed the 3 costs there, final stage cost, our 3 costs. So the lowest total cost is this one. So my lowest and my optimal path for optimal unit commitment problem is this. From hour 0, I will come to hour 1. I will stay at the same state, okay, 100. At the 2nd hour, I have to change my state to 101, and hour 3, I will again come back to my first hour, first status, which is 100. So that said, that concludes the discussion here. So that concludes the discussion of unit commitment problem. Okay, but again, as I mentioned, at the end of the economic load dispatch problem, this unit commitment problem is, again, as you know, that the unit commitment problem itself involves economic load dispatch problem as a sub problem. Okay, so whatever variation I discussed, whatever varieties of economic load dispatch problem can happen or is available, I discussed at the end of the lecture of economic load dispatch. That also becomes a part of discussion for unit commitment problem. Okay, so let's say if you have units run by wind or PV or biogas or any renewable energy sources, then this solution pattern will completely change. If you have hydro units, then you have to have a coordination between hydro units and thermal units. If you are considering the, let's say, the load pattern, okay, we have not considered any load, any statistics or any probability associated with the load demands. We have considered, well, if the demand is known perfectly, we have assumed that, well, we know the load demand perfectly without any probability. Okay, we have assumed that it is 100% probable that, well, in the next hour the demand will be such, let's say 200 megawatt. In the next hour the demand will be 300 megawatt without any hesitation. But in practice, basically the future demand you have to forecast by a technique known as the load forecasting technique. But in this course we are not taking this into account. But in practice you have to apply load forecasting, which involves some portion of statistics and probability involved in that. So that said, I mean, you can't be 100% assured that, well, you know the demand beforehand perfectly. So nothing is perfect in this world, nothing is ideal, but whatever solutions are being discussed here, these are very basic concepts associated with the unit commitment problem. Much more complexity and different solution algorithms. As I mentioned, we have only discussed priority list schemes and the dynamic programming method. There are other methods, mixed integer programming, mixed integer linear programming. The nature-based optimization algorithms are also applicable for solving unit commitment problem. Okay, but for the syllabus of this course, I think this basics is enough, because we have to also cover other things. Our topic is not only unit commitment, but I think flavor of unit commitment has been provided to you. So if any of you wants to further study on unit commitment issue in your higher studies, based on this basic, inshallah, you will be able to progress, I hope. Okay, so with that said, please take note of the assignment again. Your assignment is basically case number 3. Okay, case number 3. You will find some help from the book for the solution. I have talked about how to deal with the minimum uptime and downtime. Okay, how to deal with this issue. Enumeration scheme is also discussed in case 2. Only thing left is the how do you consider the hot start cost, and when do you consider it, and when do you consider the cold start cost. That is actually described here. So I hope you start the assignment. If you face any problem, you can discuss it with me. Also, you can discuss among yourselves. The solution is probably not completely explained, but the numbers are actually given. Some help is given in the book for case 3, I hope. So take help from the book, take help from the whatever resource you have. Still, if you find any problem, you can consult with me. Okay. So thank you very much. This assignment will be the substitute for quiz 2. Okay, so this assignment 1 will be the substitute for quiz 2. So the deadline for this will be up to the exam date. Okay, is it clear? So there will be no quiz 2, no separate quiz 2. Rather, this assignment for case 3 solution of unit commitment problem will be your substitute for quiz 2. Okay, so thank you very much for attending the class. I hope you have enjoyed it. So inshallah, we meet again on the next class. Assalamu alaikum.